Hello, today is January 12th, Thursday, 2017. (2:53 p.m.) So, still not going to build the show drive yet, but I have worked on some computer graphics. Let's see here. Okay, so this is S.H.O.wiki. This is the website. I've updated the graphics on the front page. As you can see, aside from the reflection, there is an animation. And so you can see in the middle, there's a red magnet. Actually, the red's representing the North Pole, and the white represents the South Pole of the magnet. And so there's this zoom out effect that goes on, going on over here, if you can see that. So, oh, gee. Okay, so we can do the full page here. All right, so this is the full page version. Maybe show it this way. All right, so anyway, so this is the just the animation, as you can see there. Let me go ahead and it looks a little bit better if you actually go to the website. So here it is. There's the URL for the website, sho.wiki/now/HQ, or you could just type sho.wiki. And let's go ahead and go to the Media Avenue. So this is the Media Avenue, and we've got some 3D animations here. There's the one you just saw. Although it's a little bit better if you have a faster computer. I'll show you that later on my desktop. So this one's all supposed to run pretty fast. But anyway, here's a graphic of the animation. So you can see here of the more advanced animation for the show drive. And you'll see this right now on the show drive's channel if you check very soon after I make this video. And so this should give you an idea of what we're going to have. So let's go ahead and disconnect the camera from here. Probably need to get a dermatologist for my fingers, but let's go ahead and pull this out. Okay, so let's go ahead and do a little bit of traveling here. Okay, so we're going to go ahead and let's go ahead and sho.wiki/3D. Okay, so let's go ahead and turn on the light there. Let's see here. Okay. Okay, so there is the animation of the regular one. See there, that should reveal the URL. Too close. Oh, that's the wrong side. There we go. So let's just go ahead and zoom out a little bit. All right, so This is the animation. As we can see here, let's just go ahead and type advanced after the slash, and we should get, there we go, that should be better. Okay, so here is the animation for the S.H.O drive. As you can see here, these yellow vectors represent magnetic field vectors, and these magnetic field vectors will be the result of the current in the S.H.O coil, producing these magnetic fields represented by the yellow vectors or yellow arrows. And then there's blue arrows representing the vector potential of the magnet. So you can get a various idea of what the pattern is for the vectors in the S.H.O drives magnetic field. And so there's arrows representing, for example, the forces, the magnetic field that is going to be acting on the magnet. So sometimes the camera zooms in, because I have it scripted motion for the camera, and it kind of zooms in, or actually travels and goes into the magnet in this case, revealing little vectors that are inside, representing weaker magnetic fields that are inside, that are acting on the magnet from the current's magnetic field. So of course inside the magnetic field is strong, but that's from the magnet, but then there's weak magnetic fields acting on the magnet from the magnetic fields of the current. Okay, so all these arrows here represent only those magnetic fields and magnetic vector potentials of the current. It is not factoring in the magnetic fields and magnetic vector potential due to the magnet. Okay, now the magnetic vector potential is a quantity. It's a vector field, and you can take the curl operator on the vector potential to get the magnetic field. And so that's why it's interesting, because you can do that because magnetic fields, as far as we know, they do not have divergence in their field vectors. So basically lines in equals lines out. Okay, so it's completely a rotational magnetic, rotational vector field. Okay, the yellow vectors are. That means they have, there's no sink or source of these vectors, if you will. The divergence of the magnetic field is zero. And so you can treat it as a curl of another vector field, and that can be the magnetic vector potential you can see here. Of course, you can add a gradient dependent vector field to the vector potential and not affect whatsoever the value of the resultant magnetic field that occurs by applying a curl on it. If you want to go ahead, and we could go to S.H.O.wiki. Now, I bit my tongue a couple days ago, so that's probably why I sound a little bit weird. Okay, so sho.wiki/3d/simple. So this is the simple version, the older version of that. Okay, so yeah, all right. And recent changes, I have uploaded some additional images. Oh, right. Upload log. Okay, so here's an example. This is just more detail as far as just a static image. As you can see here, this red magnet, or red section of the magnet represents the North Pole. The white section here represents the South Pole. And these curved tubes represent copper wire. And the yellow vectors here represent the magnetic field vectors, and the cyan vectors represent the magnetic vector potential, or blue vectors. As you can see, these blue vectors follow the path of the current in the wire down here as well. We got that. Anyway, so there's that. Okay. So just more pictures. I finally uploaded this one. This is just a graphic of a slightly older S.H.O coil design. Let's go ahead and go to Media Avenue. And over here, we can see the advanced version again by clicking on here, and we can enter this page. So there it is. And each time this magnet rotates a certain amount, then it turns off because the induction of the lines of flux of the permanent magnet through the S.H.O coils cancels out when it's in that strictly horizontal position. And this is just, well, I timed the animation, so this is not a full direct simulation of the magnet rotating through the S.H.O coil. It's just an animation, and the field vectors are actually generated through programming. So for example, okay. All right. Let's go to okay. So this is the code for the program. As you can see, so we're actually calculating the magnetic fields and the vector potential as well. This one's a little different than the other, but it should be pretty much the same as long as we're far away from each segment. You know, we have so many segments that the distance from the segment is much greater than the length of each segment, so that should be okay. Anyway, have some alerts that I commented out, and so on and so forth. Okay, and then this is the code that I use to switch the field on and off. So it's not a full simulation, although that would be nice to have that. I think I'm really pushing the limits though of the software now, because this is WebGL, so you should be able to play it on your phone. If it's a smartphone, it might support some WebGL. Most computers support WebGL, so that shouldn't be a problem for you. Okay, so let me just go ahead and do a little short view of this thing here. I've uploaded the thing for the smallocracy, so this is the side project again. This is really cool because you can see what you can do with 3D animations. You can adjust the sky. There's these plugins you can use and it's using THREE.js. That's a JavaScript library that you can use to do these sorts of animations. Just the inclination, luminance, me scattering coefficient. So you can do it like, make it look like Mars or something. What you can do. So like in Mars, the sky's a little bit weird. If I do it like that. Yeah. Anyway, well, the ground obviously is not responding yet because I haven't figured that out. I don't know why it's not responding. But yeah, over here is the hub towers. These are the other towers. I still have to figure out how to string these platforms together. It's gonna have to be some kind of catenary or something, or catenary. Biting my tongue at work kind of swallowed my tongue, so it's kind of hard to pronounce things. Anyway, so that's that. So I also updated the page at Frontier Fork. And so there is the animation over there. Okay. Anyway. So let's go ahead and go back over to could take out the trash, but whatever. Okay, take it out later. Okay, so down on the floor, as you might have been able to see, I have something to test with here. So let's go ahead and let's turn on the light here. A little bit brighter, get some better views. Okay. All right, so there's the microphone. Okay, so over here we have, bring this down. Okay, so this is an inverter. This is what I'll be using to power the camera if I have to run it outside. So let's just go ahead and look at this meter here. This is a X-Tech 411 multimeter. It's a 2RS multimeter for electrical measurements. So let's go ahead and turn this on. So right now it's measuring no current coming out of the 12-volt battery. Doing this, it's just going to produce a direct current. So let's go ahead now, and we see here, let's go ahead and zoom out. Let's make this a little nicer. So this is the switch for the inverter, so I'll just turn it on. All right, so I have the red clip on the meter, from the meter to the battery, and then I also have the from the battery to the meter, and from the meter to this clip over here. So let's just go ahead and turn it on. Okay, now we have some current that's showing up on this meter here, 0.32 amps. Okay, that's direct current. Now, obviously, if we're going to measure at a alternating current, we're not going to see anything. If we turn this on, let's see what happens. It shouldn't really show anything like that. It should just continue to show nothing. It shouldn't be any alternating current unless there's like some kind of noise coming out the back or something. But it's just going 3 and 4. If I turn this off, it's like there's no response. It doesn't even see anything. Let's say I put it at a lower setting here, a more sensitive setting again, 0.3 at the 200 milliamp setting, so like really nothing. Right? So that's that for that. Now let's go ahead and plug in the camcorder into the outlet here. So this is the Canon camcorder plug, as you can see here. Okay, so we're just going to go ahead and plug this in. All right, so this is off. We'll go ahead and plug this in. All right, turn this on. Okay, so let's see here. I haven't turned it on yet. So let's go ahead and, first of all, let's pull this out first and we'll plug it in while this is on. Okay. Okay. 0.31 is the number of amps this is using right now. Now we plug this in. Now we have 0.73 or 0.75. So let's go ahead and, so that more than doubled the power consumption. Well, current consumption here. We're going to have to show the voltage as well in the process. So we're going to show the voltage without the load and with the load. If we can somehow get it clipped properly on there. We're going to have to change the setting for that. So anyway, let's go ahead and measure that voltage. Let's go ahead and turn it off. Pull this out, just to be sure. And we want to remove this one, remove this one. All right, now definitely don't want this in here. We need it to be swapped around. Then we need this one here. And then we need to make sure this is on this side, not touching the other side. And same thing with over here. We don't want it to be crossing over. Okay? So obviously that was kind of dumb. But yeah, it has a high impedance inside this, so it didn't get any current going through very much. So anyway, let's go ahead and turn on the setting for the voltage. Okay. So right now it's measuring 12.7 volts. So let's go ahead. The voltage goes down because of the internal resistance of the battery, although it might not be that much of a drop. Here it's 12.6 volts. That's after we had run this. Now let's go ahead, plug this in. Okay, let's go ahead and run this first. So the voltage dropped 12.5. Let's go ahead and turn this off again. 12.6, wait for a few seconds, still 12.6, let's turn it on, 12.5 already. As you can see, the current has dropped the voltage just a little bit because it increased the internal resistance. Because of the internal resistance of the battery, there's a voltage drop, that's what I meant to say. So let's go ahead and draw some more current from here. As soon as we hooked up the camera to this device, we more or less, slightly more than doubled our voltage drop relative to what it was. So instead of going from 12.6 to 12.5, it's going from 12.6 to 12.3. So it's a 0.3 drop versus a 0.1 drop compared without this. Let's go ahead and show you in case if you didn't see that. Okay, but 12.3, if I pull this out, there's 12.4, and then there's 12.5 with the thing off. So that shouldn't be any big deal. Okay. So it gives you an idea of, yeah, there's a voltage drop when we're attaching the camera to this. Let's do a calculator. So it was something like what was it? Like 0.75 amps draw times it was 12.3 when we had it hooked up. So that's 9 watts, 0.225, and keep in mind that's with this recording. Okay, so we're recording here, and that's with the LCD and the camera. So one of the things I could do. Well, I don't want to turn it off necessarily. Okay. Anyway, 9.225, or let's just say 9 watts with the camera. Now with 12.6 with the battery. So when I didn't have the camera hooked up, but I had the inverter on, that was 12.4. No, it was 12.5, right? So let's go ahead and turn on the inverter just to be sure. Well, okay, so 12.5 right there. Okay, with the inverter on. And so we were going to multiply that by whatever the current was. I don't remember that, so I have to check again. Turn that off. We want to go ahead and turn this off. We want to pull this out. We'll go ahead and do this. Probably should have done that first. That would have been safer. Let's go ahead and put this over here. And this over here. Put that down there. Put this on the other side. And measure the direct current. Right now there's none. Okay, turn it on. Okay. So there is 0.03 amps of the current. And then you multiply that. I know it was different earlier, but anyway. So 0.3 times 12.5. So 3.75 watts, or almost 4 watts, when we're just running the inverter, and it was like what, 9 something watts with the camera connected. So difference between just under 4 versus just over 9, it's going to be something over 5 watts that this camcorder is using as a result. And of course, when the camcorder is running, it's drawing more current, and so there's additional wattage loss in the battery because of the increased current through that internal resistance. Okay, so yeah, that is pretty much all I wanted to say about that. Of course, we want to disconnect that like so. The reason why I'm going to be setting this up is so that way when I go ahead and test drive the S.H.O drive outside, we won't have this situation where I have to hook up the camera to some outlet or something. I can have it run for several hours at a time, and that shouldn't be limiting then the duration of the test. I can do, say, on a beach or somewhere out there where there's no plugs. Now, keep in mind that shows there's a limitation here for the energy of the battery. I can go ahead and show you based upon So this is the old S.H.O drive plan. Let's go ahead and look over here. let's build the show drive. I made this presentation months ago. Like, see here, alligator equipment leads. This is also on the S.H.O wiki, or S.H.O.wiki website. So if you want to go over there, and it's still going to do pretty much the same kind of testing with these things. You know, measurement the heat, the current, the voltage, etc., etc. So let's go ahead and look for, what are we looking for? Oh, that's what I'm supposed to do. Oh, right. It's like it's over the very end. Okay, so basically, in order to supply energy to the adapter in the form of alternating current, I purchased the Best-Tech 300 watt 12 volt to 110 volt AC inverter from Best-Tech via Amazon.com. Okay, so to supply energy from the adapter, to the adapter from alternating current. So I had the clips and everything. I had to attach a 12 volt battery, and so on and so forth. So basically, this 12 volt battery is rated at 7 ampere hours based upon 20 hours of steady electrical discharge. Okay. This means it can deliver 84 watt hours of energy, or about 300 kilojoules, or over a 20-hour period, an average of 4.2 watts. Okay, so basically, that's at 4.2 watts. So if we're drawing a little more than twice that amount, okay, so 84 watt hours, that is the result of taking 12 volts and multiplying by 7 ampere hours. That's 70 plus 14 watt hours, or 84 watt hours. Okay? Now we're about 300 kilojoules, and that's over a 20-hour period that it's rated to discharge, so 4.2 watts. Now, if I draw more than that, there is going to be a slightly greater energy loss due to turtle resistance, but we saw that wasn't that much when we just doubled the wattage. So the voltage went from, like, say 12.5 to 12.3 as we had measured it. So it's not really that big of a difference as far as the efficiency of what kind of energy we can actually deliver out of the battery, drawing it that quickly. So 20 hours, if you draw it twice as fast, that would be about 10 hours, which, you know, should be over 8 hours for our recording. So, yeah, so to record stable video of the show drive from a distance, I will attach the camcorder tripod. Yeah, so you get the idea. There's some other things I want to show before I go ahead and build a show drive some other day. Such a procrastinator, but every day I procrastinate, I develop something new. So let's go ahead, turn this off a little bit. Sunset. Okay. Oh, well, that's stupid. You want to see it. Okay, so magnetic fields of the show coils. All right, so this is the high-tech version. Okay, so there's a build test summary that we've got to go on here. We're gonna have to prep the shaft, cut some acrylic rods for the supports. Those are these rods that I have to cut. There's more of these that I have to cut. These acrylic rods, and they will be banded on the show drive crate to elevate these coils. These coils will be folded here. These coils will be folded in a way that better matches what you see in that video. So we fold the coils, we're gonna add hooks, we're gonna add magnets and panels. The panels are from these things here. We're just gonna hook these on to the rods. so they, are supported, acrylic on acrylic, So there it is. We're going to attach a fan, which will help also to dampen any vibrations. We're going to have a tachometer reading off of a disc. So that disc is this disc. So this is the disc for the tachometer. I'm going to put some electrical tape. Not electrical, reflective tape on there for the reading. I'm going to have a switch that's going to be attached to it, and I'm going to have a resistor, and then we're going to do our testing. Along the way, we're going to do our tests. We're going to test our old coils, inductance and resistance, folded coil inductance and resistance, new coil inductance, resistance, and induced voltage, and go to test the resistor in line with the switch, so that way we can have a consistent resistance-based voltage drop measurement. So resistance times current gives us a resistive voltage drop. As long as our resistor is consistent resistance that doesn't change with the current that much, then we should be able to calculate that appropriately. Now it's a resistor rated up to 50 watts. Let's see if I can just go ahead and bring those out here. Where is that? Well, that might be something I need to look for, but I do have resistors that I need to get for this. That would be a good idea. It'd be a very good idea to have that, the resistors, so we can actually do that. That's great. Maybe a good idea to have those resistors. It's probably in here, I guess. Oh, that's good. Wouldn't be in there. The switches probably. Should have put it there somewhere. What are we doing? Where's the resistors? Nice. I think it might be, no, it's not there. Nice, 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 nice. Okay, whatever. I'll go ahead and find that later. But yeah, cool. This is no editing policy. It's awesome. So you just get to see everything. So anyway, this is the S.H.O coil length marking. This will be used to help fold the S.H.O coils properly. So basically different lengths of the S.H.O coils need to be folded at different amounts. So I've made it this template to help me do that. And this is based upon a updated S.H.O coil rendering on the computer. So this is what it looks like. S.H.O coil template. And then magnet rotor construction. This is going to be the stack layout for the magnets. I talked about that in multiple videos. Let me go ahead and plug this into the wall. Okay, and so this is the layout for that magnet on the shaft. And so basically, you know, why would the S.H.O drive work? Too much to talk about right now, but there it is. Okay. Yeah. So anyway, that should be it for now. Today is Thursday, January 12th, 2017. I would like to thank you for your time and have a wonderful day. Okay, just a quick thing here. Got the resistors. It was in the drawer. Yeah, that's all. Yeah, time is 3:40. That's it. That's what I was trying to say. It's 50 watts resistor. So it can handle high amount of current. Should be the same resistance. You know what? Let's go ahead and measure it now. I've done this a couple of months ago, last year. But let's go ahead and measure it. Okay, so this is our 2 ohm setting with nothing attached, of course. So I'm going to have to go ahead and attach something here. I'm going to have to attach these cables. Not these ones. So, all we have to do, take these out. Alright. Let's go ahead and plug these black ones in into the one side here, and then red ones on the other. So it measures voltage and current simultaneously so that it can calculate the resistance. So what it does, it supplies a voltage to the system. It measures the current supplied, and then as a result, as you can see here, there is no resistance between these leads. Over here, there's like a minuscule amount of that, but it's nothing. As far as 2 ohms are concerned, we don't see anything on the chart here. If I disconnect this, then nothing. All right. So what we're gonna do, it's really simple. We're gonna measure the resistance of this, and I've got another one that's supposed to be the same. Let's go ahead and measure these. Okay. So it was 0.991 ohms, according to this, 0.991 ohms. Okay. As you can see there. And so, another thing we're going to do, you know what, I'm going to keep this separate so that way you know I'm switching in. Okay, maybe you should have seen it too. 0.991 ohms. Okay. Let's go ahead and disconnect this thing. And we'll connect the other thing, the other resistor. Okay. Also 0.991 ohms. See here, 0.991 ohms. Okay, that's that. How about this? Trying to see if there's any possibility of sleight of hand. Whatever I'm measuring here, obviously is not over there, so no way to fake it this time. Okay. What the heck? All right. Okay. What's going on? Oh, duh. No wonder. Stupid. Okay, there we go. 0.992. Okay? Okay, so that should be it. I would like to thank you for your time and have a wonderful day.